Hello everybody. Today I want to talk about spectrum representation. So spectrum representation is a neat way to show sinusoids that have cosines or sines with different frequencies. So phasor addition last time required the sinusoid to have all the same frequency, but this time we have this representation so that we can see all of the frequencies that make up a certain sinusoid. So, yeah, this is just a great way to represent sinusoids in a concise way. And so first, we're going to go through why we can represent sinusoids in this way before actually seeing how it looks like in our example. Okay? So first of all, we need to remember that if a signal is real, it can be represented as this. So it's going to have a DC term, which is represented by A naught, and that's where F sub k is 0. That's why our summation is going from k equals 1 to however many sines or cosines make up this signal, okay? And this signal, although it's just represented by x of t, it can be v of t, I of t, or anything that really oscillates or has this kind of motion. So in this case, technically, like we have x of t, and if it had the definition typically associated with x, and that is distance, this could be thought of as maybe as a spring. Okay? But what's super important is that this equation can actually be represented in complex exponentials. So this same idea can be represented with this equation. And so what's different here is that we take the real part of cosine is considered the real part of the Euler identity, right? And if you can recall, the Euler identity is e to the j theta is equal to cosine theta plus j sine theta. And in this case, we can define our theta to equal 2 pi f sub k t plus. And so we are looking specifically at cosine theta, right? And a sub k is just some arbitrary constant multiplied from the front. And there's this, parentheses. But I'm going to leave that off for now because it's kind of ugly. And so this is the real kicker right here. The very important portion is that we can represent the sinusoid in the frequency domain. And if we remember that cosine theta furthermore can be represented like this, so the powers are split between the positive side and the negative side of the frequencies, right? And remember, this theta right here is represents this in this case, okay? And for the time being, just for representation's sake, or for derivation's sake really, I'm not including the phasor, because the reality of this is that we're going to have an outside thing that takes up the phase, right? The phi sub k, this portion right here, which is represented in this equation fully, okay? Now, we want to go ahead and replace this portion right here with this right here. So we can write the same equation, x of t is actually equal to x naught plus n k equals 1 x k over 2. Okay, this is important. It's half the frequency because we're moving to one side a negative frequency, which is physically impossible, but it's still there. Okay, just like how imaginary numbers are not really numbers, but we still use them because they encode different information. And then we're going to have the complex conjugate of the complex phasor, because this complex phasor goes with this negative frequency, like so. And so this is the proof. So this proves right here that we can write, and I'm just going to give a little snippet of what a spectrum actually looks like so that we can visualize this. A spectrum typically is plotted with f in hertz, right? Or it could be radians per second if you're doing it in radial frequency, like that. But typically I'm going to be doing it in hertz because that's more intuitive. And then it will have a DC component right here at 0 hertz, which is going to be represented by this phasor right here. And we're going to have different harmonics, right? So different sidebands of frequencies, and they're just going to shoot straight up like this, right? And if you look at this from the side, and these are supposed to be equal. And if you look at this from the side, you can actually see, I'm going to try my best to draw this kind of 3D, but you can see that, that's terrible. You can see that there's a sinusoid, and I'm trying, and the reason why it's getting smaller is because I'm just trying to draw it out. Like, I'm not very good at this, but it looks like this, right? So it's actually representing. So if you had a side view of this spectrum, it actually will look like this. So we have this very tall one right here, and we're going to say that we have max amplitude right there, and then it's just like this. And then we have this sine wave right here, or cosine wave, whichever one it may be, like this, right? And it could be at a different frequency. Actually, technically, it's going to be a higher frequency because we can say that's 10, 20, and 30. So it's going to be twice as much here, and then with a less amplitude, right? Because the amplitude is smaller. And then finally we have 30 hertz right here, and it's a lot smaller, right? Like this. But this is not nice to look at. It's actually nicer. You get a better feel of this sinusoid if you can just see it plotted against frequency. And so let's go ahead and do a practice problem. So here's the practice problem. We're given we're given this sinusoid right here. It has a DC component, so no oscillation here, and it has two cosines attached to it at different radial frequencies right here and different phases. And we're asked to plot this in the frequency domain, and for our purposes we're going to be plotting it in hertz. So the first step we're going to do is we're going to try to represent this right here. So we want to get this x sub k divided by 2, and we want the complex conjugate x sub k divided by 2 as well, because we're effectively moving the energy, splitting them between the two sides. Okay. And we also want to find the frequencies because we want to plot this against hertz. So we're going to say get x of k over 2, x complex conjugate x of k over 2, and frequencies. So x sub 1 is actually just going to be 5e to the 0, okay? Because the reality of this is that there's no frequency, and because there's no frequency, it's a DC bias like this. And our frequency is just 0 hertz. Or, sorry, this is that was wrong. This is the phi. There's no phi because there's no cosine right here. Yeah, I misspoke. And then we have x sub 2 is equal to, now let's think about this. We're going to say, we're going to call this a naught, right, to be in line with our notation right here, this x naught, or this a naught right here. Technically, well, no, it would still be a naught in this case. And then we want to find this x sub k right here, and this is a1, and this is a2, and we want to find the half of the complex phasor, basically half of the complex phasor and half of the complex phasor conjugate. And so for x sub 2 divided by 2, but I'm just going to call it x sub 2, so hopefully that doesn't confuse you guys. But we're going to get 16 divided by 2, which is just 8 e to the j 15 degrees, because that's the phase that we have right here, plus 15 degrees. And then our f2 is going to be, now remember that this portion right here is 2 pi f sub k t, but in this case it would be f sub 1 because we're looking at the a1 term. And so we just need to divide this by 2 pi, and so we're going to get 20 hertz. And then this is super easy. We just have to get the complex conjugate portion, and it's just going to be 8e to the j. And remember, every time you see this j when you're doing the complex conjugate, you have to put a negative sign. And then our frequency conjugate is just going to be negative 20 hertz. And now this is not proper right here. I'm just doing this so that we can denote. I don't want to say f3 because that would be confusing real fast. We're going to have so many frequencies where in reality it's just the negative of it. Actually, probably a better representation would just say that this is negative f sub 2, but then this would be positive. So that's just me writing it like that. And then we have to do x sub 3. We're going to take this 20 right here. It's our a sub from our phasor, and or from our amplitude. Our amplitude, the phasor has the amplitude in it, so we're going to get 10 e to the, and then the phase is 65 j. Oh, actually, let's make this a little more interesting. Make it negative 65 degrees right there. So our first one is actually going to be negative 65 degrees. And the conjugate of that is going to be 10e j to 65 degrees. And then our frequency, 20 pi divided by 2 pi is just 10 hertz. And then we have negative 10 hertz on the other side of the scale of the plot. Now that we have all of the frequencies, right, all of the frequencies and all of the phasors, half phasors, we can go ahead and plot this. So step 2 would be to plot. So we would draw this big spectrum right here, and it's going to be in f, hertz, frequency, hertz. And we will have this y-axis, but we're not going to have any units in this case because we're never told what the units were, so it's just going to be AU for arbitrary units. But once again, this could be voltage, this could be current, etc., etc. Now let's go ahead and plot it. So we have a spike at, we have a DC bias or a DC component. And so we're going to write that right here. And it's good practice to write what the half phasor or the phasor is in this case. Okay. The next thing that we're going to have is this 10, right? The 10 hertz. So we're going to partition this -10, -20, 10, and 20. And we're going to draw our phasors, draw our spikes, sorry. And right here, we're going to have a pretty tall spike. And then the same identical spike is going to be on this side. And this is going to be 10, right? The amplitude is 10. E to the -j 65 degrees, because we originally, in the real part, we have -65 degrees, but in the negative frequency part, we have a positive 65 degrees to be the counterpart. And then finally, we get to plot the last set, this 20 hertz right here, like this. And so once again, make sure that you line up the positive frequency with the correct phase, okay? And you can see here that that the negative doesn't mean that the frequency is negative. It means whatever has been put in this argument right here. And so we're going to put 8e to the -j 15 degrees over here, and 8ej to the 15 degrees right here. And that's basically it. We're going to be using frequency domain a lot. Signals and Systems uses frequency domain a lot because it's very nice to represent these. And once we get into modulation, like multiplying sinusoids together, it'll be very useful to see what's actually inside those sinusoids. And a good way to visually see that is through this spectrum representation. Probably the only thing that I haven't really talked about properly is where cosine theta equals this. And I would encourage you to derive it from Euler's equation. It's quite simple. All you have to do is make sure that you have this cosine theta by itself. Remove this sine theta. I did do this derivation in one of the circuit analysis videos, so feel free to go check that out too. And that's it for spectrum representation.